Okay, so if there are no more questions, I will just start with the topic for today, which is process synchronization. And today we're going to look at the different algorithms on how you can synchronize processes in operating systems. Okay, so last time we were talking about how processes can run concurrently and how they can run in parallel, right? So depending on how they can run, of course, you might get some issues with those processes. Obviously, if two processes run at the same time and they try to update the same data structure in your operating system, that might start some issues, right? So what might be possible issues if two processes try to update the same data or the same memory location? Any ideas? Yes, exactly. So you might get into the situations where, let's say, you expect a data to be in a specific memory location, you check it, but apparently some other process went in this location, deleted it, or did something about it. Okay? So for this reason, obviously, you need the processes to be able to get synchronized in some way. Okay? And it is also very important how you synchronize them. If you synchronize them in a way that they constantly send messages between them with information at which point they are, this might be hard, because imagine you have a process, it edits a file, and then this process has to send information to all other processes in the operating system and notify them that they do that. So this is not very efficient, and for this reason today we're going to look at some algorithms that you can use to solve this issue, right? Okay, so now I'm going to just give you a simple example with the producer and the consumer programs that we learned last time. Okay, we even did a practical exercise on them, so you should be familiar with those. So let's imagine that we have a buffer, and in this buffer we have two processes. One of them is adding information to the buffer, the other one is taking information from the buffer. So let's say that the producer, in order to keep track on what's added and what's taken, let's say we create a variable called counter. Okay, so when we add information to the buffer, we're going to increment the counter with 1. So counter plus plus means counter plus 1. Okay, so let's say if in that situation the counter is 2, counter plus plus will make the counter equal to what number? 3. Exactly. Okay, and on the other side, let's say we have a consumer process and exactly the opposite. We're having a counter, so once the consumer takes data from our buffer, the counter is decremented with 1. So, very simple. If I first run the producer, then the consumer, everything should work fine, right? But how about if I run the processes concurrently? Okay, so if I send both of those to the memory, okay, and they run at the same time. So here's what is going to happen. Okay, so let's say at the same time I send to the register the producer and the consumer. Okay, so in that way, when I send the producer process, we're going to have that the register 1 will be equal to counter. Then when the process performs something, the register will be equal to register 1 plus 1. Okay, and then the counter will be equal to its new value, the value of the register. And in the opposite way, we're going to send the other consumer process to the register. So register 2 equal to counter, register 2 equal to register 2 minus 1. Okay, so we decrement, and then the counter is equal to register 2. So that way we update the register and we update the counter. So if you run this with threads, with multiple threads, right? So we run it at the same time, okay? And let's say we start the thread of the producer first, and we start the thread of the consumer second, okay? But still they are sent in the register at the same time. So if that happens, then the value of the counter is going to be updated in the following way by the operating system. So first of all, again, you can see here, let's say the counter value is equal to 5, okay? So the first thread is going to update it to 6, right? So the counter will increase with 1, and the producer will add some value or some data to the memory. Then when we go to the consumer, since the consumer is executed with the same in the same time on a different thread, okay, the counter value will not record this result 6. It will still be equal to 5, okay, because we call those processes into threads. So it will be decreased with 4, okay. So then, if we have a code that is firstly making the counter value equal to register 1, okay, then our counter will be equal to 6. And after that, let's say the other thread is saying, okay, counter equals to register 2. Then the first result will be overwritten, and our counter now will be 4. Okay? So you can see what is happening. Those operations are just run or executed concurrently. Okay? So what is the true value of the counter in the end? Yeah, the true value, the actual value. So obviously, each thread is giving us different value of the counter, right? So thread 1 is giving us 6, thread 2 is giving us 4. So both of those cannot be true, right? So there is some error. What is the actual value of the counter? What do you think?
1.
1? No. Okay. No, it's not 4. Any other suggestions? So imagine this in your mind, okay? You have a memory location, right? And in this memory location we have 5 elements, counter equals to 5. Then we have one thread that is adding one element, okay? And then we have one thread that is taking one element. So how many elements are left? 5, okay? So the actual answer of this question is 5, because the producer produces one element on our buffer or on the memory location, and then the consumer is taking one element. Okay? So because the threads are running concurrently, this means that the counter value, firstly, it will be incremented to 6 by one of the threads, and then it will be decremented to 4 by the other thread. Okay? Imagine those threads. Thread 1 doesn't know that counter increased to 6, and thread 2 doesn't know that the counter reduced to 4. Okay, so it really depends which value of the counter gets updated first. You will get a different result, but it's going to be wrong at any time. Okay, so this brings us to one very interesting thing, which is true for every program that is running in the operating system. So every program at some point, yeah, you can come in. So every program at some point might want to read, write into files, or perform other things on a memory that is shared with other processes. Okay? Also, at other times, a program can perform tasks that are not related to writing into a memory or anything like this, that the other processes don't care about what the program is doing. So when we have a process that goes into shared memory and does something there, okay, we say that the process is in its critical section. Okay, so critical section is the segment of a program, so you can imagine it as a part of the code, okay, that is accessing shared memory. So when you have a process that is in the critical section, you need to do some scheduling with the rest of the processes in the operating system. So you make sure that the location at which the process is working is locked and no other process can access it. Okay? So if we talk and if we think about processes as different sections of code, some of those are related to critical section, updating something, some of those are not. We can then divide the code that builds our process into three sections. The entry section, which is the code before going into the critical section, okay? The exit section, which is the code after the critical section. And then we have the remaining section, which is the rest of the code that is not related with shared memory. So obviously the job of the entry section is going to be to set up everything to make sure that the memory location is free to use, okay? And the entry section will also make sure to take this part of the memory so we can write information or read information from it. The exit section is going to release the memory to the other processes so then they can use that part of your memory. And obviously the critical section is going to be the part when you're updating and you're performing some actions to this section. And this is how it looks really in C. It's very simple, okay? So we have the entry section, okay? There is some rule. Based on this rule, the process might enter in the critical section. And once the process does its job, then we perform the exit section. And finally, we go to the remaining section of the code. And of course, we're going to go over a few algorithms that are doing that, but this is a very basic description of how we have entry, exit, and critical section. So, for example, let's say while the turn is equal to the current process, then we go to the critical section, okay? And actually, so while the turn is equal to j, means that we're waiting, okay? So we're process I. So let's say we're process I, and we want to change some memory, okay? We want to go into some memory and change things. So while the turn is equal to another process, to the process j, we are going to do nothing. We're just going to wait and stay there and just wait for the memory to be free. So then if we have another process, okay, so the process j, once process j is completed, they can turn the turn to process I. So they'll have in the exit section, turn equals to I. Then process I that is waiting here, okay, will see that it's no longer j's turn. It will execute the critical section, and then it will give the turn back to j if j has something else to do in their critical section. This is the most basic explanation. Of course, we're going to look into the algorithms, and after that, of course, it will execute the remainder section. Okay? Any questions so far? Now, when we are working with critical sections, okay, we need to follow some rules. Okay, so how do we decide if an algorithm that is providing the process with the ability to share memory location, how do we find out if the algorithm is good that is doing that? How we make sure that the synchronization between the processes is good and it's actually going to make sure that we don't write in the same memory at the same time? So we have three basic rules. The first one is the rule for the mutual exclusion. We need to make sure when one process is in its critical section, then no other process can perform tasks in the same critical section. Okay, we need to make sure that this is the case. Okay. The second one is the progress. We need to, yes, that specific part of memory. So this means that if, let's say, we have two processes that want to reach the same memory location, only one can do it. Okay, the other one can work somewhere else. Yes.
If J is in its critical section, I can't be in its.
Exactly. That's pretty much it. Yeah. Okay. The next rule is progress. So, with simple words, we need to make sure that there is no process that is in its critical section indefinitely. So there is no process that can take the memory forever and never release it. Okay? Is the second. Okay. And the third rule is that so once we have a process in the critical section, okay, we need to make sure that the critical section is available for all the processes. Okay, so every process can go into this critical section and actually verify what they can verify whether they can go in the critical section or not. Okay, they should all be able to access the algorithm to do so. Okay, so now let's look at the first algorithm, okay, which is going to show us. Oh, actually, before that, we need to make sure that we have a good understanding on the different type of kernels and kernel processes, right? Okay, so as you can see, there are two types of kernel processes. The first one is preemptive, and then non-preemptive. So the preemptive processes are those that we can jump to them, okay, and then swap them with other processes all the time. Okay, so let's say we start process A and process B. We do a little bit work in process A, okay, then we release the resources to process B, then we go back to process A. Those are preemptive processes. The non-preemptive processes, they are going to run until they are completed, and then they're going to exit the kernel mode. Okay, they're going to do that voluntarily. So this means that if a process goes into the kernel mode, okay, they're going to complete their work, and after that they're going to get out. Okay, so normally for the non-preemptive processes, obviously, once they go to the kernel mode, they're just running until they execute and they complete. Okay, so we need to focus more on the preemptive processes, which means those processes that can get swapped into the memory. Okay, so those processes, they really need to make sure that once they access a memory location, they can release it, then another process can access the same memory location, and so on, okay, since they're more dynamic. So for those, we normally need to apply those algorithms for the critical sections. All right, so the first algorithm that we're going to talk about is called the Patterson solution. Okay, and in the Patterson solution, you're having pretty much two variables, okay, that are called turn and flag. So turn means that it's the process turn to make a decision whether they want to go to their critical section or not. Okay, and then the flag right here is showing if the process actually is in the critical section or not. And I will show you how this is implemented right here. So, flag I equals to true means that the process is ready to go into their critical section. Okay? Turn J means that it is the turn of process J to go into their critical section. Okay, so the flag identifies, am I ready to go into the critical section? The turn shows whose is the time to make a decision, whether to go or not. Okay, so how the Patterson algorithm works. So let's say we have two processes that they want to use the same memory, process I and process J. Okay, so let's say this is the code for the process I. So the process I will do. So first of all, the process I will say, okay, I'm ready to go into my critical section. Okay, so I will turn the turn to true. After that, before going into my critical section, I will set the turn equal to J. So now it's J time to decide, okay, whether they want to go or not. And J can run exactly the same algorithm, okay? So once we say it's J's turn, then we're continuously going to loop until the flag J is equal to true, okay, and it's J's turn. Okay, so imagine now we shift the responsibility to process J, okay, and if the process J has the flag J equal to true and it's their turn as we set it, okay, they will go in their critical section. But at some point, let's say now it's I's turn, okay, for some reason we pass this while loop here, so obviously we run into another process. The other process says, okay, it's process I turn, okay, so we shifted the turn to us. We already set our flag that we are ready to go into the critical section, and we go to our critical section. Now we finish our critical section, and then the flag here, we're going to set it now to false, because we no longer need to go into our critical section since it is completed, right? We completed our critical section. We changed something in the memory, and that's it. So once we did that, we're going to set this to false, okay? And now process J, okay, will be able to assess their critical section because we just went out of ours, okay? So imagine if you apply this methodology to two processes that want to assess the same memory location, okay, they can have some sort of scheduling without the need to explicitly send messages to one another, okay? They can just both run this function, okay? And that way they can make sure that they allocate the memory to one another and not run concurrently at the same time into the same memory, okay? And actually this algorithm is going to be one of the algorithms that we're going to implement it in Python. And so as I said, today we're just going to do threading, and then in a future lecture we're going to use threading to show you how two processes can use this algorithm in order to be scheduled and assess the same memory location at different times automatically, okay? The idea of this software is that everything happens automatically. So obviously this implementation has one weakness, right? It can only work with two processes, because in the section where we run process I, we explicitly specify J, right? We specify the other process location or identifier, wherever. Okay, in the process J, we need to specify process I. So this works only for two processes. Yes? Say? A queue. So normally, obviously, if so they are not stored like in a specific queue per se. I mean, processes, they can be specified with queue, of course. But when you think about memory, let's say if one process is accessing the memory, obviously the other one has to wait somewhere. So if you have more than one process, then you can implement a queue where you can stack the processes. But here we just have one that probably you can implement it with a queue that will have just a single element, right? So of course, while one of the processes is accessing the memory, the other one is going to wait, right? And it will wait by staying in this while loop right here. So here in this while loop, we'll continuously be looping and looping and looping until the other process finish their critical section, because this is the only way that they will change their flag to false. Okay. So this is going to be, so right now this process pi, right? So once we exit this while statement here, process I will go in the critical section. Okay. So once either the flag j is equal to false or it is not j's turn, then process I will go into their critical section. So if we think about it, if it is not j's turn, this means it is I turn, right? Okay. So I already set it to the flag that is ready, correct? Okay. So now we have that I set the flag that is ready, and also it is I's turn because it's no longer j's turn. So then I goes into the critical section. Okay.
Why?
I know, it's because this is in the inner level and you're thinking, okay, while this is happening, are we constantly going in the critical section? Is this? No, so how it's implemented there is while flag, yeah, so while this condition is correct, okay, we're just looping without moving forward in the code, okay? So this is, we're getting a little bit confused because it's not Python, right?
Yeah.
You're expecting if it's in the inner level to be within the while loop,
Oh,
but this is C, right?
Semicolon.
Exactly. So you can imagine, while this is true, nothing is happening, we're just looping, nothing is happening, this doesn't get executed, okay? We're just stuck here, okay? And
The second it becomes not true, then it moves to the
exactly.
because it's allowed to continue.
Exactly. So we're going to loop here until some other process does something, okay? So now it's j's turn, okay? And the flag of j is equal to true. Probably the other process already set it, right? Exactly. It's my turn to do action.
Yeah.
One is showing whether I'm ready. The other thing is showing whether it's my turn to do action. Okay, so let's take a few scenarios, right? Let's say process I wants to edit the critical section and process J didn't start it yet. Okay, so we have just that. So what's going to happen now? We're going to set the flag I to true. We're going to set the turn to J, okay? But when we go to this while here, okay, if J never even started, then the turn J here is going to be none, right? So this while loop will just do one iteration and then we'll continue in the critical section, right? And this makes sense because if we have no other process that wants to access the same memory location, we can access it immediately. So right, this means AND. So both of those need to be true in order to constantly loop in the while loop. Okay? So if there is no process J, flag J will never be equal to true, and this while loop will do one iteration. Okay, it will exit it, will go to the critical section because there is no other process trying to access this critical section. However, if there is process J, and let's say they start at the same time, okay, we're going to set our to true. We're going to turn the turn to J. Then at the same time, the J will turn their flag to true. And then J will turn the turn to I. Okay? So now we have flag I equals to true, flag J equals to true. Now it's I's turn. Okay? And then I will enter the critical section. Yes. So when you run them at the same point of time, obviously, one of them is going to be tiny milliseconds faster than the other, right? So what's going to happen actually, you're going to make the turn equal to I, and then immediately you're going to make it equal to J from the other process. Whoever gets first. okay? So maybe I will get first to it, okay? And then j will override the turn I, okay? Just 1 second, and I will get to. So, okay, let's say here, this is equal to true, this is equal to true. There cannot be overwriting here on the first line, correct? Okay. On the second one, let's say turn equal I, here turn equal j, can they be overridden? They can be, right? So j process will send the turn to I, and then I immediately will turn the turn back to j, okay? This is what will happen in the actual life, okay? And here in this while loop, okay, we're going to wait only while the turn is still equal to I, but this overrided, correct? Okay, so since this overrided, okay, now it's I's turn, okay, this while loop is broken because both conditions need to be true, okay, so since it is broken, now j is going in the critical section, correct? And I is going into a while loop where it wants to make sure that it's not the flag j is true, okay, which it is true, okay, and it's going to loop while it is turn j, okay? So as you can see, it transferred the turn here, correct? Okay, so it's gonna loop while this process goes to a critical section. Then if you can see, in the end of the critical section, the process will do flag, yes. So now it will make flag j equal to false. The while loop in j will break, correct?
It's done.
Yes. And now j will go through the critical section. Okay? You had a question? So exactly, the important thing when you want to schedule processes is to have an algorithm with a variable, okay, that will specify which turn it is, okay? A unique variable that will shift the turn to one process or the other one. And you can see here how those two processes, they can never run their critical section together, right? Because either one of them is going to loop in the while loop, while the other one will execute the critical section, or the other way around, okay? If you're not convinced, I can give you a task to try at home to break it. So far, nobody ever broke it, so yeah, it is. So it has one chance until the critical section is executed on both sides. Because if you think about it, if it's, let's say, I turn, okay, then j, imagine how we're going through the lines. J will stay here. It cannot exit away from the while loop. It's just going to be waiting until I completes, right? It can never exit. It cannot go in the beginning of the code to overwrite everything again. And even if it will still give the turn to the other process, right?
Okay.
So the only way that one of the processes go to the critical section is if the other process release this critical section. It lets the other process to go there, because only the other process can set the turn to the first one, right? Only I can set the turn to j. Only j can set the turn to I. Okay, it's you need to a little bit wrap your head around it, but this is why we're also going to do a practical exercise so you can really see how it works. Okay, yeah, so I mean, those are pretty much the things that we were talking about. We covered all the cases. Now, the good thing about the Patterson solution is that it is applicable and it covers all the criteria for making processes able to schedule themselves. The negative side is that it is applicable only for two processes, right? So with the Patterson solution, you can schedule only two processes. So obviously we need some way to schedule any type of processes, okay, and to make sure that when one process takes resources, then the other processes cannot do that. And to do that, we have the concept of locking, okay? So when we say that a resource is locked, this means that a process is using it and no other process can actually access it, So if we try to lock a resource in a single process, in a single processor system, this is easy because the processes run one after another, okay, and they don't run concurrently on different cores. But obviously, when you have multiple cores, you can run things at the same time. And for this reason, you want to make sure that a resource is locked. So after that, another process cannot access it. Okay. So when we work with many processes, we want to add some hardware instructions into our operating system, okay, that are able to schedule those processes, okay, and those can be atomic, which means non-interruptible, okay. So those can run in the background when we create any type of process. Those instructions start working for the process, so any resources that the process takes cannot be taken by other processes. Okay. Okay. So the first solution for when working with multiple processes is called the test and set instruction. Okay. So the test and set instruction is working in the following way. The idea is that this target here is the resource that we want to lock, okay? And so we want to lock and we want to check or test if it is locked. This is why it's called test and set. So you're testing if the resource is locked, and if it is not locked, it is locked by you. Okay? How it works? First of all, let's say that 0 means that the resource is free, 1 means that the resource is busy. So here is the resource value. Okay? So if the resource is free, as I said, this value here is going to be equal to 0. Okay? So if a process wants to access this memory location, what they will do? First of all, they will create a temporary variable that will be equal to the value of the lock, whether the resource is locked or not. Okay. Then they are going to set the value of the lock to true, which means they will set the value to lock, regardless whether the previous value was true or not. Okay. And after that, they are going to return the original value of the lock. Okay. So this is also something that we need to wrap a little bit our heads. Jesus Christ, why I'm saying hands? Heads around it. So let's say our process is unlocked. Okay, so we have a free resource, which means that the target will be equal to 0. Okay, so here the temporary variable will be equal to target, temporary variable will be equal to 0, correct?
Yeah.
Okay. After that, we're gonna set the lock, okay, we're gonna set the location to true, which means we're gonna lock the memory location, okay? And after that, we're going to return the previous value of the memory location, which was unlocked, right? Okay. Just put this in your mind for a second. Okay, now see this. So if the process was unlocked, the test and set function will set the lock to 1, so it will lock the process, and it will return 0, because it will return the previous variable of the lock, which was 0 initially, right? So then in this while loop, so if it is 0, we're going to break the while loop, and we're going to enter the critical section, right? if it is 1, we're not going to enter it, because this means if this function returns 1, this means that the resource has already been locked. Okay, so we're just going to loop here until this becomes 0. Okay, so okay, now let's see if the target resource was locked previously, which means target is equal to 1. What's gonna happen? Temporary variable will be equal to 1, correct? Yeah. Then the target variable will make it equal to true. It was already true, but we're gonna make it true again. Then we're gonna return this time 1, correct? Okay. So now we didn't change anything on the lock because it was already locked. We already couldn't use it. So we just keep it 1. But this function also returns 1. Okay? So basically, no matter how many processes are using this function, and they can be many of those, it will always return 0 if we can take the resource, and it will always return 1 if the resource was already busy. Do we agree on that? Or did you understand it? Or you need a little bit more time for me to explain? Did you get it, guys? There? Yeah? How about on the back? Here on the front? Did you understand? Yeah? Okay. So this means that no matter how many processes access this section, we can always make sure that if the lock is equal to 0, we can take it, so this while loop will break, and we can go to the critical section. So obviously once we go to the critical section and we finish it, we want to release the resource. Okay? So we're gonna make it equal back to 0. So then when the next process want to access the same resource, okay, they will find it equal to 0, and then they can enter their critical section. Okay, so the other function that can also be used for multiple processes when they try to access the same memory is called compare and swap. Okay, so in the compare and swap function, you add a few values. Okay, so you add the log value, which now can be higher than 1. It can be any number. You will add a value to which you're going to compare the log, okay, and you're going to add a new value. Okay, so once you enter the function, you can create a temporary variable that is equal to the value of the log, and then if the value of the log is equal to the value that you expect the log has, okay, then you're gonna update the value of the log to the new value, and you're going to take it. Okay, and the new value is provided by you. Then if another process wants to access it, okay, they will not be able to do so. Okay, so guys, as I was saying, here imagine again we're having this while loop, okay, and the only way that we break out of this while loop is if here we have a value that is higher than 0, or actually value that is equal to 0, right? So we want this function, so if this function returns 0, okay, the while loop will get broken, correct? Because those two will be equal, so it will break. So the expected value of our lock here is equal to 0. So this is what we expect. And then we also add our lock right here. Okay. So when we do that, you can see that when we return the temporary variable, right here. So if the lock is in fact equal to 0, okay, it will get updated. So on the next interaction, it will have a different value. So this temporary will no longer be equal to 0. Okay? And in that way, once we break the while loop here, obviously again we can go to the critical section. And once we go through the critical section, we can again set the lock to 0, so no other process can use it. So as you saw, the test and set and the swap functions might be a little bit confusing, right? So you really need to think a lot about how they work, you know, to really think in a way that many processes are running those functions dynamically, obviously. So obviously there is a more simple way to run multiple processes, and those are called mutex locks. Okay, so those locks are actually very simple, and they run two functions: acquire and release. Acquire means that we're taking the lock, and release means that we're releasing the lock for somebody else to use it. Okay, so let me see if I have those functions so I can show them to you. Okay, so as you can see, it's very simple. In the acquire function, okay, we're going to say while the lock is not available, okay, so while available is equal to false, we're going to loop continuously. When another process runs release on the same lock, they will make available equal to true, right? So then here in the acquire, this while loop will break, okay, and we will set available equal to false, which means that we're taking now the lock. So this would be a more simple solution that you can implement. So in the acquire, we are constantly checking whether the resource is available. If it is available, we make it equal to false, which means that we're taking it. In the release, we simply set the available variable or the resource equal to true, so we release the resource. That way, if we want to go into our critical section, what we're going to do is, so first of all, we're going to run the acquire function. We're going to start waiting until the lock is available. Once it is available, we're going to go to our critical section, and once we go on our critical section, then we're going to release the lock. So you can see that if we really start thinking in terms of locks, unlocking resources, you can actually have this elegant solution that is very straightforward to implement. The only disadvantage here is that you can have something, I don't know if you've heard about it, it's called spin lock. So spin lock means, you've heard something? Yeah?
That sounds familiar.
Yeah. So, yeah, if you heard it, but you don't really know what this is, it is actually very simple. Spin lock is happening exactly in this situation. So the problem with acquire and release is that a process will constantly loop until the resource is available. So imagine you have 5 processes that want to access the same memory location. One of them assesses the location, the other 4 are hanging right here in this while loop, and they're waiting. So while they're waiting, they're taking obviously memory, right? They're taking computing resources, and they're just waiting for the resource to be available. So they're all praying and saying, let's go, I want this resource, just release it and I can start using it. Okay? So it's really up to the process that took the resource to whether release it or not. And this is called spin lock, when a process is waiting while another process is using the resource. And obviously here, if you don't have some timeout or some other variable that specifies how long we can wait, we can wait indefinitely depending on, of course, the other process. Okay? Yes.
Okay.
Yes.
Only to make the process.
Exactly, exactly. So this is when you create, let's say, a new process, okay? When the process tries to enter some critical sections to update something, some of those functions, they get activated. And of course, this is mainly done on multi-core systems when you have multiple processes running at the same time, trying to access the same thing.